to go.
Okay. Okay, so this is Project A2, and just as in the one that John just talked about, this started as an EPA STAR grant for Lynn and me, and we've had previous students working on that, and we have several current students making the transition to this center work. So I'm going to get us started here, and then actually there's, including myself, 4 of us involved in this brief presentation. So Isabella and Keith coming soon. So this is where we are on this. Again, we're still working on some of the development stuff, but have definitely done some piloting on this, and I'll show you, or we will show you some of that in here. And the primary work we've done to date is on fluoride, but the work that we're just beginning is on these other inorganics, particularly arsenic. There was just an article published in the last week in the Austin American Statesman about arsenic in Texas drinking waters. So this is a timely subject for us. Again, this is the graphic that we're all going to show, and we're really going to show you work in both of these first 2 boxes. There's been no published papers at this point on this, but we have given several presentations at ACS and actually earlier some other work as well. We are scheduled to probably give one of the webinars that's involved in WINS and D-risk in the next year or so. So that's on that. And this is the presentation that we're going to give you this morning. Isabella is going to talk about alum coagulation for fluoride removal and show you a little bit of the bench scale stuff that we've done, both with synthetic waters and natural waters, but probably a greater fraction of her talk will be on the pilot study testing. We've done 2 pilot studies, one in West Texas, McKenzie Lake, with kind of an amazing water with high fluoride concentration and high NOM concentration. And then work in A2 Springs, Colorado, which is actually quite near Boulder. So a few of our students were out there last summer, including Isabella. And then the waters are very different, so it's interesting to see what those are like, although both have high natural fluoride concentrations. And then Key will talk about her recent work in the last few months on moving from alum into iron coagulation, looking at how that might be used for fluoride removal as well. And then Lynn will look ahead to work that we're starting, looking at other trace metals, and again with a particular emphasis on arsenic in there. So that's where we are headed in the next minutes or so, and I'm going to turn it over to Isabella. Isabella is a master's student in our program and been working with Lynn and me on this since she came a year and a half ago.
Hello. So I'm going to start talking about some synthetic water tests that we ran. This is the recipe for the synthetic water that we made. It's about 3 milliequivalents per liter of alkalinity and hardness and 14 millimolar of ionic strength. We used 3 different natural organic matter surrogates: phthalic acid, pyromolytic acid, and salicylic acid. And in the test, we varied the pH and the coagulant dose, but we're primarily showing tests with a varied dose, but we'll have a little bit of pH variation too. So from these tests, we found that fluoride removal was not significantly impacted by the presence of the surrogates. They're all fairly similar, but the organics removal was impacted by the presence of fluoride. So the lilac color is just pyromolytic, and then the pink is in the presence of fluoride, and so at all the doses, you can see that the removal is a little lower. And the same for phthalic acid at 100 milligrams per liter and 200 milligrams per liter of alum. Aluminum residuals were also impacted by the presence of the different ligands. So at the bottom is a purely alum solution, and then the residuals show a decreasing trend with increasing alum dose, which we think is due to the formation of a mixed precipitate. So the aluminum to ligand ratio being lower would produce maybe a more mixed precipitate that would deviate from the traditional solubility, and then at the higher aluminum to ligand ratios could be a more pure aluminum hydroxide solid that would then more closely follow the solubility. But an important note is that at the lower doses, the secondary MCL for aluminum is violated, so the residuals are above 0.2 milligrams per liter, which would violate the regulation, but 200 milligrams per liter alum and above were all below the SMCL. So we also had some natural waters that we used sodium carbonate to add alkalinity in the Colorado water. Yeah. So we, in the Texas one we didn't because it was sufficient, but we definitely added alkalinity in the Colorado. Sorry. And the aluminum residuals followed the same trend that we saw in the synthetic water tests, decreasing with increasing alum dose. And the residuals were pretty much the same as well here as they were in the synthetic waters. And again, the same trend with the secondary MCL, only 200 milligrams per liter and above satisfied the 0.2 milligram per liter limit. So moving into the pilot studies, we did pilot studies at both of the small water systems that provided us with natural water, so Mackenzie Lake and Manitou Springs. And in the pilot study at Mackenzie Lake, we didn't control the pH because it had high enough alkalinity to maintain the value at a reasonable pH level throughout the tests. But in Manitou Springs, we did control it using that sodium carbonate, so giving alkalinity and controlling the pH at 6.5, and we ran one test at 7.5. And the Manitou Springs facility itself uses sodium carbonate to bring the pH back up, or for pH control in their own system, so that was, we matched our process to theirs as much as we could. This is a picture of Mackenzie Lake, Texas. It's near Silverton. And this is a picture of the setup. So we had our influent drum, and then it went through the flocculation basin, and we also started with a sedimentation basin at the end. So this is some data for steady state. The system reached steady state around an hour, and then the sedimentation basin didn't really provide any extra treatment benefit, and so for consideration of time, because it added a lot of time to the process, we stopped using the sedimentation basin, because it really was pretty identical to the flocculation basin effluent. So for the fluoride removals, these are a few of the results that we had. We got around 50% removal at the 300 milligram per liter dose from a little bit higher influent of 3.48, and the system reaches steady state again very quickly and stays pretty constant throughout, so we definitely were able to achieve good removals, and it was an effective method of defluoridation, and 20 milligram per liter, the low dose, was a very, very low removal, lower than what we saw in the jar and the synthetic water tests. This is the complete set of results that we found. So the maximum removal was 56%, which brought us to 1.57 milligrams per liter, which is just above the World Health Organization recommended limit of 1.5 milligrams per liter. And we also saw very low organic removals, max around 24%. And this deviation could probably be because the lack of pH control. Our jar tests were all controlled at the same pH, and this one wasn't, so that could be a pretty big impact. But we still were able to get below 2 milligrams per liter, so the current secondary MCL for fluoride. This is the reservoir that feeds the Manitou Springs, Colorado system. It's at the base of Pikes Peak. And this is the picture of the actual water treatment facility where we stayed. We were in a little room right in that corner. And this is the setup. So we had pretty much the same instruments, the influent drum and then the flocculation basin, but again, we didn't need the sedimentation basin after what we discovered at the Texas pilot study. So these are the results from here. We got much higher fluoride removals than in the Texas pilot study. around 80% at 300 milligrams per liter, and we got to 53% the max Texas removal at around 100 milligrams per liter of alum here. And we also had much higher organic removals, around 66%. So these match, again, very closely with what we saw in the Colorado water jar tests and the synthetic water jar tests. But we also studied silica. So the Colorado water has an influent concentration of about 10 milligrams per liter silica, and we ended up running some tests on that and found the maximum we got around 34% removal, so we're getting some silica removal. And another interesting note is that previously in the jar test, we only got below the aluminum SMCL at 200 milligrams per liter alum, but here we reached it at 100 milligrams per liter alum, so at an earlier dose. And at 100 milligrams per liter, satisfying that SMCL and with the 53% fluoride removal, that brought us down to below 1.5 milligrams per liter of fluoride, because the influent fluoride concentration during this testing was around 2.7 milligrams per liter fluoride. So we're getting to pretty low fluoride concentrations, so we're pretty confident that we can meet new treatment guidelines. And we're also getting good organic removal as well at the same time. So we ran one other test at pH 7.5 to look at optimization, and it had a significant impact on treatment. And so the fluoride removal dropped 20% below 6.5 when just going up to pH 7.5, and the organic removal also is decreased. But interestingly, the silica removal was greatly increased. So we saw the opposite trend, so that was an interesting fact that we noted. But it just highlights the importance of pH control on the process, and also confirms probably why the Texas pilot study removals were much lower than what we saw in the lab. This is a summary of all of the different fluoride removals across the synthetic waters and the natural waters and the pilot studies. And so they all agree fairly well. The pilot studies were usually either matched or, especially at the higher doses, a little bit lower than what we saw in the jar tests for synthetic and natural. But really the only main difference was in the Texas pilot, it was so low, but again, we did not pH control that pilot study, so that could be why it was so much lower. But we're getting very high fluoride removals at the higher alum doses, and good removals too at doses closer around 100 milligrams per liter. So we're really happy with that. And overall, alum was definitely effective at defluoridation, and pH 6.5 is what we found to be kind of the optimum pH of removal. And the impact of natural organic matter on fluoride is pretty minimal, but pilot tests in Colorado were consistent across the board, very little deviation between the synthetic and the natural water tests, which was cool. And pilot tests were lower, again, probably due to differences in pH. And also it highlights the importance in background water chemistry. So the Texas water had a really high alkalinity, higher TOC, and a lower SUVA value, and so the type of organic matter and the background composition and matrix of your water also has a pretty significant impact on the process and the removals. But with that, the next part will be ferric. So Key's gonna talk about ferric.
So while he comes up and we'll talk about this, I just wanted to kind of give a little context that I probably should have given before. Come on up. Fluoride, the MCL at the moment is 4 milligrams per liter, but the WHO guidelines are 1.5 milligrams per liter, and EPA announced almost 3 years ago now that they're reevaluating, and we expect them to go down to probably 2 or 1.5. They won't say anything, but that's kind of the expectation. And so this work is going to be a lot more important if that MCL is changed than it appears right now.
Yeah.
And the other thing I wanted to mention is that we're also going to talk this afternoon. We're going to be talking about natural organic matter, and the natural organic matter removal within this process will be talked about in greater detail later.
Is there some reason you didn't go ahead and filter all of these? It's just to save time? What happens when you filter a water that's had 300 milligrams of alum thrown at it?
These are all filtered.
Oh, those are the filtered
Yeah,
numbers?
so
you didn't settle?
In the pilot test, the first one we did sedimentation, and you know, it worked reasonably well, but in terms of fluoride, it didn't make any difference. So
Okay.
since
Yeah.
fluoride was our primary interest, we just kind of cut it out for the later tests. But obviously, if you're using doses of 150 to 300 milligrams per liter, you have a lot of sludge. I mean, there's a huge sludge.
There's a huge residual
Yeah.
problem.
Yeah.
Yes, there is, no question. But the thinking behind this was that a small system that might be more willing to put up with a greater amount of sludge than to put in a completely different process for fluoride removal, if this process would work. And your book tells me you're very skeptical, and I understand that's
The sludge handling.
Sludge can drive the front end.
Yeah.
Yeah.
And we'll find it over and over again. And when you get, I mean, it's become, you feel like running a softball plant here, you got huge volumes of sludge.
Yeah,
running out.
you have a huge volume of sludge.
Yeah,
No question.
it's a,
I mean, was the driver for this if you're already,
Yes.
you
Yeah.
already had removing fluoride,
No,
and
you're already-
basically jacking up the dose in response to the EPA lowering? Okay.
Yeah.
And I don't think our goal is to get to 300 milligrams per liter.
Hopefully, unless you're an alum salesman.
So I think, you know, looking at the higher doses was just to determine whether the trends held.
Yeah.
Right.
no, I get that, but even at 100, you're pretty high.
Yeah.
Yeah. I know.
Yeah.
Mhm.
Yeah, our hope was actually, initially, you know, that we could get there with something closer to 50. But, you know, you have to run all the way through.
No,
and-
I get that.
I mean, yeah, at some point, the OpEx costs of dealing with the sludge is clearly gonna overweigh
Way
a new
overwhelm.
process, whether it's,
Exactly.
you know,
Yep.
ion exchange and
Yep.
electrochemical.
Yeah, we understand. Okay.
So, hi, I'm Kia. I'm a first year PhD student here at UT Austin. So today I'm going to talk about the ferric chloride coagulations, which I've just started, and also the continuing research of alum coagulations. So what I've wanted to do could be these four objectives here. So first thing is to quantify fluoride remover in ion coagulation systems. And the second thing is to determine the effect of natural organic matter and also the effect of natural organic matter surrogates on fluoride remover. And the last thing is to determine the effect of fluoride on the organic acid remover. So what I'm working on is this bench scale testing. So I'm using synthetic water, which is the just same conditions with the alum coagulation case. And the pH of each jar is varied from pH 4.0 to 6.5, and the increment of pH is 0.5. So the coagulant ferric chloride dose was controlled as 100 milligram per liter and 200 milligram per liter. So I've been using potamolytic acid and phthalic acid as my NAM surrogates, and I've also used the NAM. So here's the first results. It's about comparison of co-precipitation versus preformed ferric hydroxides. So if you see the data of preformed tests, the percent of fluoride remover decreases as pH increasing. So there's an interesting thing for the co-precipitation test results, and there's a clear peak at pH 4.5 for both cases with different ferric chloride doses. And I assume, and I suppose that this is because of the ferric and fluoride complexations. So here's the ferric and fluoride complexation graph. And if you see the particular species FAF2 and positively 1 charged species, and it shows the peak between pH 4 and 5. So I assume that particular species is somehow a key player for the ferric coagulation process. So move on to the effect of organic acids on fluoride remover. There is not significantly difference causing by the presence of organic acids. So phthalic acids and NAM shows pretty similar trends with the pH of all the pH range. And the interesting thing is that at pH 4.0, potamolytic has more remover compared to the rest of the case. And I think this is because of the surface area of that flux formed in the jar. So here are the figures of each jars at pH 4.0. So as you can see in this figures, you can see more clear like more flux, visible flux in the bottom-leaded case. Now I've been working on to figure out what is really going on this particular pH, and this is gonna be my one of my future work. So from now we're gonna look at the organic acid removers. So first thing is phthalic acids. The left side data was measured by UV vis, and right side is TOC. So as you can see, in higher pH, especially above the 5.0, there is less remover. The remover percentages decrease as pH increases. And especially for TOC data at that pH range, the organic acid remover decreases with the presence of fluorides. And the interesting thing of this phthalic cases is at pH 4.5, there is more removed when they are with the fluorides. So I think must be something happen in pH 4 and 4.5, and I still need to figure out what is going on in this pH. And the next thing is the other non-surrogates, polymalonic acids. So both data shows the decrease of organic acid remover when the polymalonic is coexisted with the fluorides, but the little bit more decrease in the TOC data here. And the other thing is the remover percentage of each pH are pretty consistent. So next thing is remover of non. So above the pH 5.0, there's a slightly decrease as pH increase, but not so much difference. But if you see the UV vis data at pH 4.0 and 4.5, there is decreasing of organic acid remover when NOM is with the fluoride in the system. So here's the conclusion of this ferric coagulation so far. So the first thing is the fluoride in the system is removed up to maximum 30% at pH 4.5. And there's no significant reductions in the remover due to the presence of organic acids. And the effect of fluoride on organic acid remover is depend on the types of organic acids and also the pH. So compared to the alum coagulations, ferric coagulation shows more organic remover over the entire pH range. And the thing is, maximum fluoride remover happens at the lower pH, like ferric chloride shows maximum remover at pH 4.5 compared to the pH 6.5 for alum cases. So this is my end of presentation, so I'll pass it to the Dr. Lynn Katz.
So, throughout a lot of our work with coagulation and the aluminum and iron solids, one of the goals has been to really understand not so much can we get to a dose of 200 milligrams per liter or 100 milligrams per liter, which may not be where we want to go, but to really understand what will happen in systems that are already existing, and if there's any benefit, for example, to reducing the pH. So if you take, for example, the Texas water, where we didn't get very good removal, perhaps adjustment of pH, we could get a reasonable enough removal at a low enough dose to be able to not have to implement another technology. So it isn't, so the looking, at across doses is really to get a better understanding of the mechanisms. One of the things that we have learned through this process, and Mitch is going to talk about this a little bit later in terms of looking at organic removal, is that the interaction of these anions, organic acid anions, humic ions, and trace metal ions, has a big effect on the formation of alum flux and their characteristics. So the next step of what made up of the granular ferric hydroxides, mostly hydrous ferric oxide, and the E33 is mostly like a goethite surface. So we ran a bunch of different experiments on this. We got data in both single solute and bisolute data. We did titrations of this data, tritium exchange of these materials, and from that we were able to fit titration data, where we're basically just taking the surface and adding acid or base and fitting this. So we fit both the GFH and the E33, and what I want to show is that we can develop models that predict adsorption in complicated systems. So for example, these are all the single solute systems of arsenic, silica, and calcium for both sorbents. So this was, some of this data was fit, some of it's predicted, but the concept is that's the single solute. We then looked at solute systems, so these are total predictions, and we were able to capture the trends with a simple model like the diffuse layer model. We're able to look at the effect of adding silica to the system and looking at the removal of arsenic and calcium. So we can see the effect of both cations and anions. Okay. We also then went, just to show this, that we actually went to a trisolute system where now we have arsenic, silica, calcium, and I should say this is really we also have carbonate in the system too, at about 0.01 molar. And so as a result, you can see, we're capturing at least the trends in these very complicated systems. So we're very confident that we can at least get to a point where we can tell you what will end up happening when you start looking at systems where you have both background cations and anions and trace metals that you want to look at. And that was sort of the goal of, I lost my, others. That's it. So I think that ends the presentations for project A, whatever.
Me too. Great. I'm almost did. Okay, so thank you. That's terrific. So we've fallen, we're sliding a little bit behind, but not too badly. And so I think next up we've got Trevor.